Welcome back to AUTS. In this video, we'll be going over rotational equilibrium, which describes a situation where an object doesn't rotate and is stationary. Very similar to Newton's first law, where an object in rest stays in rest, but in rotational equilibrium, it's a bit more specific. It focuses on the rotational aspect, so it means the torques must be balanced. The net torque has to be 0. Alright, so let's look at an example of rotational equilibrium. The complete equilibrium needs two conditions. Net force is 0 and net torque is 0. If net force is not 0, that means there's going to be an acceleration, right? And if net torque is not 0, that means it's going to be rotational motion. So balance about any point requires the sum of the counterclockwise torques to be the sum of the clockwise torques, because they all have to balance out, right? And make 0. So let's try an example of how this could look like as a problem. A 1 kg rock hangs from the left end, so at the 0 mark here, of a uniform stick supported at its 1/4 mark. The stick's center of mass is at the 1/2 mark. Find the mass of the stick. Okay. So that we know that this is in rotational equilibrium, right? And both of these objects are not moving. So that means the torques here are equal. So we know torques are measured from centers of masses, right? So the torque of this object is going to be measured from its center of mass, which is the halfway point. I mean, in a regular ruler, it'd be the halfway point. Now it looks a bit more to the 1/4 of this. Anyway, so at 0, right, we have 1 kg. 1 kg times, what's the force here going to be? The force times the length of the object. How far is it away from the fulcrum point, which is L/4, right? And this is not just a force, remember, right? 1 kg is not a force, we need the actual force, which is going to be 9.8 meter per second squared. Because that's mg, right? So 1 kg times g is 9.8 meter per second squared downward. So 9.8 L/4 is equal to the mass of the stick, right? Concentrated at 1/2 center of mass, which is just the L/4 away. And that should be it, right? Because this is in meters. This mass, I have to put an mg here, but once I put that, it's good. So then, if I was to just do 1 kg times 9.8 times L/4, right? Because, so actually let me write this a bit more properly. 1 kg times 9.8, because mg is the force gravity acting down here, right? That's the force. And then, remember, torque was force times distance, right? So this times distance, which is L/4. It's L/4 distance from the fulcrum point. Now that has to be equal to the counter torque provided here, right? Because this is providing in the one. If it goes like this, that's what direction? Remember, right? That's counterclockwise. But here we're going clockwise. So this has to be equal to, at L/4 away, what's the force here? mg. And we know, why is it L/4? Because we measure torque from the center of mass, okay? That's why I went over center of mass in my last video. So that times mg. So big M, we don't know what big M is, but we know what g is, right? Times 9.81. So what we can do here is we can cancel out the L/force and the g's. And what are we left with? 1 kg is equal to m, which is the mass of the stick. So that's how you'd solve problems like that, okay? That involve rotational equilibrium. And they're asking you more about each, block and stuff. So now let's have some practice regarding rotational equilibrium. A 2 kg mass hangs 0.6 meters left of a pivot. Okay. 2 kg mass, 0.6 meters left of a pivot. Where right of the pivot must a 3 kg mass hang to balance? Okay, so the force here is 2 kg times g, because it's mg, right? Times 0.6 meters, which is the distance here, is equal to, well, we don't know the distance here, distance times 3 kg times 9.8. So 9.8 and g cancel out. I could have probably written this as g either. That's fine. And then we know that d is equal to 2 kgs times 0.6 meters divided by 3 kgs. So 2 times 0.6 divided by 3, or 0.4 meters to the right. Okay, that's what's going to give you rotational equilibrium. Over here, a 4-meter plank that weighs 200 newtons rests on a support 1 meter from its left end. Okay, so it's a 4-meter plank, but it rests on a support that's 1 meter from its left end. So 1 meter here, and the rest would be 3 meters, right? A child sits on the far left end. What child weight balances it? Okay, so we know the mass here, or the torque here, is going to come from the center of mass, which is at 2 meters, because that's always how it works for a scale, right? Or a ruler. 2 meters. It's the correct center of the object. And the weight is 200 newtons, right? So 200 newtons is times, what's the meters here? Times 1 meter, right? Because it's 1 meter distance away from the fulcrum, 2 meters away, is equal to the weight of this child, which is m times 9.8 times 1 meter, right? Because it's also 1 meter away. So m is just equal to 200 divided by 9.8, or 20.41 kgs. So pretty heavy plank, I would say. That makes sense, right? Because usually if a kid sits somewhere on a plank or a seesaw, the thing's going to go up. If it's not going to go up, that means there has to be a lot of mass weighing down on this side. A seesaw is balanced. The left child, 300 newtons, sits 2 meters from the pivot. Okay. So he's sitting here. 300 newton weight, which is mg, right? And this is a force as well. I went over weight versus mass. And then the right child sits 1.5 meters from pivot. Find the right child's weight. Okay, so weight is, not mass, right? Weight is mg. So over here, 300 newtons times 2 meters has to be equal to 1.5 meters times the force, which is going to be just the weight, right? The force of gravity, just the weight. So that means 600 divided by 1.5, or 400 newtons is the weight of this child. So that's how you solve problems regarding rotational equilibrium. Now I'm going to go on to a different concept that uses this very same concept. Okay, it's built upon the exact same foundation here, which is the mobile method. and balance beams. These are problems that come up often in physics tests, and I want to make sure you're prepared for them. Okay? A mobile is a stack of balanced beams, so like this. Okay? Like imagine your rate scales, right? But they're perfectly balanced. And then a mobile is just a stack of them. You have to solve these from the bottom up, and each bar has equilibrium torque, right? Because it's not moving in any direction. So it might be a bit confusing right now, but let me show you it in action so then you can understand better. Okay? A bottom bar, the left arm 6 centimeters holds W1, right arm 4 centimeters holds 3 Newton. Top bar, left arm 8 centimeters holds the whole bottom assembly, right arm 10 centimeters holds W2. Find W1 and W2. Okay, so if this is not moving, that means this has to be in rotational equilibrium, right? Which means 3 newtons times, what is this? 0.04 meters is equal to W1 times 0.06 meters. Okay? So W, because that's just the torques here, right? Weight 1 is a force here. Force times distance from the fulcrum. Same thing. Distance from the fulcrum, force. So W1 is equal to 3 times 0.04 divided by 0.06. Or, in other words, approximately, just 2, okay? Just 2 newtons. So that's W1. Pretty straight. Now, what's the combined weight of these things? So there's 2 newtons here, right? There's 3 newtons here. So this entire thing weighs 5 newtons. There's 5 newtons here. And 5 newtons of what distance? 8 centimeters. 5 newtons times 0.08 meters is equal to 0.0, actually just 0.1 meter, because 10 centimeters is just 0.1 meter, right? Times W2. So W2 is just going to be 5 times 0.08 divided by 0.1. Or, in other words, this should give me around 4, right? It should give me exactly 4, yeah. 4 newtons. So that's how you solve mobile machines, okay? And the thing is, the more layers there are, the more difficult it equally gets. Because you can see here, right? This could get a bit complicated. You could be given one, like, weight of one planet, and then you could be asked to find the weights of all other planets if they're in rotational equilibrium. But the thing is, you don't need to worry, right? It's the same steps. This would just be the weights of this, and then over here you'd have to use that torque. This would just be the weights of these combined. Over here you'd have to use this torque. Okay? Similar. Not too bad. So, make sure you practice on these by yourselves. I'll leave you a few problems here, okay? This problem, because it's kind of hard to write out beam problems, right? You just have to look at them and do them. So take a look at this and try it out yourself. If you get the same values I got, that means you're doing good. Otherwise, you might want to look at the video again. Okay? Next video we'll be going over IMA, AMA, mechanical advantage, and levers. So make sure to look forward to that, because those play directly into torque. And thank you for watching, and welcome. You're welcome. If you could share my content and like and subscribe, that would help me push out more content as well as reach more people to help them learn physics as well as, all the other subjects. So I'd appreciate that.